So I want to continue the discussion that we began last week about injective and surjective functions, and specifically I'm going to look at what happens when we have a function f that is both surjective and injective. So f is called bijective if f is both injective and surjective. So again, remember injective, you might also see that as one-to-one. And surjective, you might also see that as onto. So try and think of some maybe basic examples of a function that's both injective and surjective. One that might be immediately obvious is, let's say that you've got f going from the natural numbers to the natural numbers, and let's define it by f of x equals, well, let's just say x. That's definitely one-to-one. If you hand me two numbers and say that f of x1 equals f of x2, well, then just by the definition, we've got x1 equals x2, so that means that f is injective, okay? And to see surjectivity, we say, well, let's just take some n in the natural numbers and ask, is there an x in the domain so that f of x equals n? And the answer is yeah, let's just take x equal to n, and then that means that f of x equals f of n equals n. So f is going to be surjective here also. I want to take us through another example. Let's take the example of a function f that maps the natural numbers to the integers, and let's define it by f of n is going to be equal to n divided by 2 if n is even, and let's define it by 1 minus n over 2 if n is odd. And actually here I'm going to specify that we're talking just about the positive natural numbers. So typically we include 0 in the natural numbers, but this time I'm going to exclude 0, and hopefully you'll be able to see why. Well, let's just go ahead and run through a few examples. And so our first number that we're going to look at is 1. So f of 1 is what? Well, since here we're saying n equals 1, so that means n is odd, which means we take the second line here. And so we plug it in, so we get 1 minus 1 over 2, which just equals 0. Okay, so f of 1 is 0. Let's see what f of 2 gives us. Well, 2 is an even number, so that means I'm going to use this top definition here to say that f of 2 gives me 2 divided by 2, which is 1. Okay? And so now we've kind of got this pattern where we're going 0, 1, -1, 2, -2. My guess would be that the next two numbers give us 3, and then -3, and then 4, -4, 5, -5, and so on. Okay, so that's kind of giving us some intuition about what this definition of f is. So now what we want to do is let's try and prove that f is actually a bijection. And so what I mean by that is we want to show that f is both injective and that f is surjective. So let's start by proving that f is injective. So how do you prove that something is injective? Well, you start by saying, let's suppose that we've got two elements in our domain that map to the same element in the codomain, or into the range. And then we show that those two elements that we started with are actually the same. So here I'm going to say let's let n1 and n2 be elements in our domain. So we're talking about the positive natural numbers here. And suppose that that f of n1 is actually equal to f of n2. our goal is to now show that n1 and n2 have to be the same element. So maybe I'll write that down here, is that our goal is to show that n1 equals n2. Okay, well, first of all, we're kind of stuck into two cases. One of those cases is going to be that f of n1 and f of n2 are going to be either positive, or they're going to be negative, or they're going to be 0. And it's going to be helpful in this case to break it up into those two cases and say, well, let's suppose first that we're negative and find out that n1 and n2 have to be the same, and then we'll suppose that it's not negative and find out that they have to be the same also. So we're kind of forced into two cases. We've got the case here where f of n1 and f of n2 are both positive. And then we've also got the case where they're not positive. And it might be confusing as to why I'm breaking it up into these two cases, but the definition of f is kind of forcing us to look at it this way. And that's because here we're putting in a positive number no matter what, right? We're putting in a positive natural number. And so if I'm plugging in a positive natural number into f, the only way that f is going to be negative is if n is odd. And we can see that by looking at, well, let's say I plug in a positive number, then that positive number divided by 2 is going to be positive. So if n is even, then f of n is going to be positive. On the other hand, if n is odd, then I've got 1 minus some number divided by 2. And since we're looking at numbers that are greater than 0, 1 minus any number in the natural numbers that's greater than 0 is going to be negative. And so this thing is going to always be negative. Negative divided by a positive is going to give me a negative number. So our definition of f kind of leads us into this natural way of thinking about splitting it up into two cases of positive and negative results. So these are our two cases when f of n1 and f of n2 are both positive, or when f of n1 and f of n2 are non-positive. So let's start off with that first case. So case 1. So we're supposing that f of n1 equals f of n2 and that thing is positive. And so again, looking back at our definition here, we're going to be positive if and only if n is even. So that means that in this case, both n1 and n2 are going to be even. Okay, so we can write that down. So then n1 and n2 are even. And so that means by the definition of f that n1 divided by 2 equals n2 divided by 2. Okay, well, that just tells us immediately by multiplying both sides by 2 that n1 equals n2. And so we're done. On the other hand, case 2 here, now we've got f of n1 and f of n2 are both negative, or are both non-positive. Okay, well that means, just looking up at our definition again, that means that n1 and n2 are both going to have to be odd. So we have that n1 and n2 are both odd, and that means that we can use our definition of f for an odd number to say that 1 minus n1 divided by 2 equals 1 minus n2 divided by 2. And that implies then multiplying both sides by 2 that we have 1 minus n1 equals 1 minus n2. And subtracting 1 from each side and multiplying by a negative 1 tells us that indeed we have n1 equal to n2. And so in both of these cases, we end up saying that n1 and n2 are equal, which means that we've shown what we wanted to prove. Now there's a slight subtlety here, and it's part of the reason why I'm specifying that we're talking about the positive natural numbers, so not including 0. And that's because there's actually a counterexample. If you include 0 in this definition here, then what would f of 0 be? Well, 0 is an even number, so that means by our definition of f, that means that we've got 0 over 2, which is just 0. But we also already showed that f of 1, since 1 is odd, we've got that as 1 minus 1 over 2, which, well, that also equals 0. And this would be a counterexample to f being injective, because then we would have f of 0 equal to f of 1. But 1 and 0 are definitely not the same. Okay? So there's a very particular reason that we talked about just the positive natural numbers, and that's because of this counterexample right here. Okay, so that shows the injectivity of f here. And now we want to show that f is surjective. To show that f is surjective, we have to start by taking an arbitrary element in the range and show that you can map to it by some element in the domain. So we have to start by saying, let's take k to be any arbitrary integer, okay? So we're given some arbitrary element here in the range, and our goal is to construct some element in the domain that maps to that element. So again, we're going to probably want to split this up into cases. Because we've got an integer, we can split it up into the case when k is positive or the case when k is negative. And so let's look at that case 1. When k is positive, well, then by the same argument that we gave earlier, that means that if we're going to be able to construct an element that maps to it, we're going to have to look for something that's even. So if k is positive, that means that if we want to find some n that makes f of n equal to k, that means that we're going to have f of n be n over 2, which means we're probably going to want to choose n to be equal to k, 2 times k. So to write it out clearly, what I'll say is, okay, if k is greater than 0, let n equal 2 times k. First thing to make sure of is this number n actually in the positive natural numbers? Well, we've got some k that's an integer and it's positive, so that means 2 times k is also going to be a positive integer, which means that it's going to be a positive natural number as well, so we're good. And we want to check that f of n actually equals k. So the first thing to see is that n is not only just a positive natural number, it's actually an even natural number. And that's because we've already written it in this form where it's 2 times some integer, which by definition makes n even. So moreover, n is even. So that means that f of n is going to be equal to n over 2. But we've said that n is 2k, so that means that that's just 2k divided by 2, which is equal to k. Great, so we've done it for the case when k is positive. Now let's look at the case when k is not positive. We have to somehow construct some n that makes it so that f of n is equal to k. And again, let's just kind of do some scratch work here. Well, if k is less than or equal to 0, we've already shown then that means that k is going to have to equal 1 minus n over 2 for some n. And so rearranging terms, that shows us that 2 times k equals 1 minus n, which means that we're going to have, well, subtracting 1 and then multiplying by negative sign, that tells us that n is going to equal 1 minus 2k. And that seems like a pretty good goal for, that seems like a pretty good candidate for what n should be. Again, one thing to check is that, is this thing actually in the positive natural numbers? And the answer is yes. Try and convince yourself of that for a second, okay? So now we've got our candidate for n. Let's check to make sure that it works. K is less than or equal to 0, and let's let n be 1 minus 2 times k. We already checked that n, because k is less than or equal to 0, n is definitely in the positive natural numbers. Okay, so that's a good start. Next, what we want to do is we want to show that f of n equals k. We have to decide first whether n is even or odd in order to apply f to it. And since we've written it as 1 minus 2k, you can think of this negative 2k as actually just 1 plus 2 times k1, where k1 equals negative k. And so that means by definition that this is an odd number, so n is going to be odd. Let's say here, since n is odd, what does the definition of f tell us? Well, that tells us that f of n equals 1 minus n divided by 2. But here, n is just 1 minus 2k, so that tells us that this is 1 minus 2k. Parentheses are important here. And, well, that just equals 2k divided by 2, which just equals k. And that shows then that in the second case, we also have surjectivity. And that ends the proof. That shows that f is surjective here. And since our previous work showed that f is injective, that shows that f is actually a bijection. Okay, that's all I want to say. Just I wanted to run through this example, give you an idea of how to prove injectivity and surjectivity, and show you an example of a bijective function that's maybe a little bit more complicated than just the examples that I gave last week. Again, there's a worksheet posted on the website, so I would encourage you to take a look at that, work through all of the examples that you can. If you have questions, come into office hours and try and find me there. And otherwise, have a great day.